So we have defined viscosity, I should say dynamic viscosity, as the ratio of shear stress to strain rate. So we said we defined this quantity which was the proportionality constant between the shear stress and the strain rate. Let's take a look at the units of this quantity. So tau is the shear stress. So it's a stress, that means it's a force per unit area. So it will have the units of newtons per meter square, which we call Pascal. And the strain rate, by definition, if I look at the dimensions, the numerator of the strain rate is a change in velocity. So the dimensions of du dy would look like meters per second, and there's a change in distance, that's meters. So the denominator has a dimension of second inverse. So my dimension of viscosity, dynamic viscosity, has a unit of Pascal over second inverse, Pascal second. Sometimes this is expressed, instead of using pascals, it's directly expressed in terms of Newton per second. So Newton meter square times second inverse. And if we plug in the idea that force is mass times acceleration, so we typically have Newton written as kg times acceleration, which is meters per second square times second inverse over meter square. So we get something like kg per meter. I made a mistake there, didn't I? Times second inverse. So that's an alternate unit that you will sometimes see, but rarely. Usually people stick to Pascal second. We should also define something called the kinematic viscosity, which is just a reframing of the dynamic viscosity mu. So this kinematic viscosity is written using the notation nu, and this is nothing but the dynamic viscosity over the density. And if you do the units, you'll find that this has units of kg per meter per second over rho, which is kg per meter cube. And so this has a unit of meter square per second. So recall that if the viscosity is a proportionality constant between the stress, the shear stress, and the strain rate, we have a strain rate unlike a strain that you encounter in solids, but conceptually it's the same. If you recall your deformable body mechanics, we typically plotted stress on the y-axis and the strain, in this case the strain rate, on the x-axis. And depending on the kind of material that we were using, we would get, if you were doing a tensile test on steel versus aluminum versus something that's really ductile, we would get different slopes in the linear region, and this is what we have called Hooke's law for solids. In this case, this slope corresponds to the dynamic viscosity of a fluid, and the higher the slope, the more the viscosity. So, for example, if we plotted the relationship between stress and strain for water and honey, then honey would be the curve with the higher slope. Now, there are also fluids where the relationship between the stress and the strain is not linear. So, it's sort of like plastic deformation in solids, where the curve sort of becomes non-linear in some fashion. That is what is called non-Newtonian behavior. So, this idea that it's a linear relationship, tau proportional to du dy, or in particular equals some constant times du dy, this is what is called Newtonian behavior. So, this is Newtonian. And when tau equals some mu du dy, where mu in turn is some complicated function of the strain rate, then this is what is called non-Newtonian behavior. And depending on how that curve looks like, so let me erase this and talk about various kinds of non-Newtonian fluids. We will not actually be working with non-Newtonian fluids much in this course, but it's a good idea to know what they are. So, if you had a fluid, a curve could look like this, or it could look like that, or it could be linear with some offset. So, these are all examples of real behavior. This curve would suggest that as you increase the strain, you need a proportionately greater, well, a disproportionately greater shear stress to shear the fluid. This is what is called a shear thickening fluid. Then there are fluids where as you increase the strain rate, as you go further along this direction, the rate of increase of the shear stress is no longer linear, and it actually, you need proportionally less shear. This is what is called shear thinning. And then there are fluids which have some kind of yield stress. You need to apply a finite amount of stress before it actually starts deforming, and then after that it actually behaves linearly. These are what are called Bingham plastics. The most common Newtonian fluids are the ones we encounter every day around us: water, air, gasoline, honey. These are all examples of Newtonian fluids where it actually exhibits just the most common behavior, which is a straight line. Non-Newtonian behavior, well, shear thickening fluids, there are things like cornstarch solutions, shear thinning fluids, let's see, ketchup, and Bingham plastics, you can imagine, let's see, toothpaste. If you look at toothpaste, toothpaste looks like a solid. It has its own shape. When you squeeze it out, it sits there in its own shape. But the moment you start spreading it, it does flow. And mayonnaise, for example, again is thick, but when you start spreading it, you find it's progressively easier to spread it. That would be an example of a shear thinning fluid. Shear thickening fluids are things, again, mostly food based. I would say batter, when you're kneading dough, initially it's quite shear. Well, the more you knead it, eventually it flows, but it takes progressively more and more energy to actually knead it as the gluten strands form. So when you're kneading dough for bread, that would be an example of a shear thickening fluid. But mostly in this course, we'll be working with water and air. Just some common values that you should always remember. For water, this is a value that you can assume if nothing's given. For air, these are two values that you may not always be given in every problem, but this is a standard value that you can assume.